Okay, now let's see if this works better. By any chance? Okay, now let's see if this works better. I have the suspicion that it is the university network system. Because when I try it from home, there's no problem at all. Well, just made it in time. Now it's working again. Yes, that looks good. I keep an eye on it, and I can only apologize for the issues. So let's try again. I think you can hear me because I can hear myself, which is not necessarily a good thing. And let's go straight into the 0 and first order reactions as long as the thing stays stable. So, and now the big question is, will it stay stable or will it go offline? Yes, it stays stable. So, right, let's try. So we said, for example, we have a reaction where A is the reactant and it is consumed. And this time we want to do that for a 0 order reaction. And I like to illustrate how this works with a little picture. And you've seen that picture because I just had it up. This is actually a Christmas present that I got from my wife. God bless her. And here is a box. Let's say I have 100 gummy bears. Does anyone like gummy bears? Yes! Nicole is very excited. Daniela, yeah, of course. Any preference in color? Red. They are all good. Yeah. I agree. This is really interesting because a lot of people say red is good. I like the dark red the best. They taste of raspberry, and that's one of my favorite flavors. Unfortunately, my daughter likes them as well, so she picks out all the red ones, and I get the left with the yellow ones, which I don't like particularly, but the white ones are good as well. Anyway, let's say I have 100 gummy bears in my box. And I make the claim that I can eat, say, 5 gummy bears GB per minute. Okay? So now I want to know from you how many gummy bears so I abbreviate them with GB. How many gummy bears would be left after, let's say, 8 minutes? How many gummy bears are left after 8 minutes? And not just the red or orange ones. Alex says none. Why none? Yes, you are absolutely right. Let's say 5 gummy bears per minute, so I start with 100. After the first minute, I take away 5, so that's 95. After another 5, after another minute, it's 90. Then after 3 minutes, I've got 85, and so on and so forth. Alex says, I will eat them all. Okay, what do you end up with, Alex, when you've eaten 100 gummy bears? Diabetes, exactly. A tummy ache, diabetes, and probably you feel really, really sick at that time. And we don't do these things. So, a dentist appointment, yeah, probably, but it doesn't work that fast. So what we have done is basically we have looked at a concentration of our gummy bears. So here, let's say these are the gummy bears, A, and here is time. Right? And let's say we start with 100 gummy bears here. And the gummy bears go down. Will they ever reach 0? Will the box ever be empty? Yes, yes, yes. So it can reach 0 here. Can it go negative? No. No, no. A negative gummy bear might exist in Star Trek, but it doesn't exist in reality. That does not make sense at all. So we come to point 0. What happens then to the gummy bears? Well, they probably stay at 0, don't they? So we have a nice curve here. And what we have here with our 5 gummy bears per minute, this is actually a rate constant. This is our rate constant, K. Okay, so how can we write the whole thing in mathematical terms? We said, let's see, will it work? Does it go offline? No, excellent. We said our rate for A, or we said we can also write this as dA over dt, which is exactly the same thing. This d just simply means it's a very, very small change. Small change in A in a very small time frame. Equals consumption. So what sign is it? Negative. Thank you, Daniela. You're right. So minus K times A to the power of 0. And this 0, that is the rate order. Now what we want to do is we want a relationship between A and time. And there is a way, I probably will do a video at one point, how you can derive the equation for that. What you basically do is you treat that as a differential equation and you integrate a little bit and things like that. And you end up with the equation for a zero-order reaction. And this equation reads A final minus A initial equals minus K times T final minus T initial. So what does this all mean? Now, our A final here, this guy here, is basically what we want to know. So for example, we want to know what is our concentration of A or gummy bears after, let's say, 15 minutes. Minus A initial and A initial, that is actually our starting point. That is how many gummy bears we start with. So that's 100. Equals minus K, and I said I eat 5 gummy bears per minute. So minus 5 per minute. T final, that would be 15 minutes. Minus the starting point. And I usually set this as 0. But I don't have to. We will see examples where it is not 0, but we just simply put that in here as 0. And now this I can very easily convert that into a linear equation. So I just simply make A15 the subject, and I have A, and I write here again A final equals minus K times, and very often we just simply write T. We say this to the time 0. Well, it's just to the time 0, it just doesn't matter really. Plus A initial. Okay? And here we have the equation for a straight line. Y equals mx plus c. And as I've done that in the previous layer, here we have A. This point here, A initial, that's our A initial. That's our starting point. And we go down up to a certain point. Remember, we can't go negative. What is K? What is our K in this case? It must be the gradient. Abi says it's the gradient. It's the gradient, yes. It's the gradient. So the gradient is K. And because the curve goes downwards, we have a negative sign here. Does that make sense? Now, a typical example for a zero-order reaction is, you wouldn't believe that, is elimination of alcohol from the bloodstream for males. This is quite important. So the elimination of alcohol from the blood for males follow a first-order reaction. What is it for females? Well, for females, we all know that females are far more complex than males. And if you agree, send me a like. Females are far more complex than male, and for them it does not follow a zero-order reaction. It's something different. So nobody agrees with me that females are more complex. Oh boy, you should be married. You'll find out that females are far more complex. Or if you're female, you already know that you're more complex. But I don't want you to hold that against me. I'm not at all sexist. I just know that for a fact that females are more complex. So, zero-order reaction. It's very simple. What we simply plot is the concentration of A versus time. And we get a straight line. We can't have negative. We can also turn it around and say, if we plot concentration versus time, and we get a straight line, then this must be a zero order. Okay? And I think that's quite important, this one here. Also, I really want you to remember this equation, A final minus A initial, and I abbreviate that because I don't want to write books. So the F stands for final, the I stands for initial, equals minus K times T final minus T initial. Okay, so I want you to remember this as well. So far, so good. So we've done the zero-order reaction, a number of eliminations of drugs from the metabolism, also for the follow a zero-order reaction. So it's not just the alcohol for males. Now, what on earth then is a first-order reaction? Again, we can look at the gummy bears I'm not showing you the gummy bears now because, you know, I'm just thinking about them. I'm salivating. And I don't want you to salivate. But let's say I start with 100 gummy bears. Again, 100 gummy bears. And here my claim is I can eat 5, no, make it 10. 10% of the gummy bears in the box in 2 minutes. Okay, so let's see how this would look like. I start with 100. So after 2 minutes, how many gummy bears are left? Ninety, 90, yes, absolutely right. So minus 10, so I've got 90 gummy bears left. Wonderful. After the next 2 minutes, how many gummy bears are left? $80. Oh, 81, 80. Now that's interesting. Okay, so I eat 10% of the gummy bears that are left. What's the 10% of 90? That's 9. So I've got 81 gummy bears left. So after the next 2 minutes, how many gummy bears are left? How many gummy bears are left? Josh says 73. Alex says 72.9. I don't know whether you can have 0.9 gummy bears. Let's round them up to 73, as Josh suggested. Next 2 minutes. Well, so here we had 8. Here we have minus 7. So we would have, after the next 2 minutes, we would have 67. 66 rather. Or 65.7. How would our curve look like? So if I do my gummy bears here, concentration of A versus time, would it still be a straight line? Yeah, it looks like a fat guy. Would it be a straight line? Michael says it's an exponential decay curve. That's interesting. What does that mean, Michael? Actually, you are absolutely right. It goes towards 0. So let's see. Here is my starting point. These are my 100 gummy bears. But it would not be a straight line. It would look like something like that. And Michael, you're absolutely right. It tends towards 0. Does it ever reach 0? Strictly speaking, it will never reach 0. At least when we are working with concentrations. When we work with gummy bears, the problem is that probably you end up with half a gummy bear and then a quarter of a gummy bear and then a millionth part of a gummy bear. And by that time, it's probably, you know, it melted away or something like that. But technically speaking, we will never reach 0. Remember, 0 order, we easily can reach 0. That's not a problem at all. So how can we actually put that into some mathematical concept? So, again we have A, and we can write dA over dt equals minus k times a to the power of 1, because that is our 0 order reaction. And now we have to transform that into what is called the integrated form. You don't need to know how this is done, so don't worry about it. But the equation for the integrated form of this rate equation here is ln A final minus ln A initial equals minus k times T final minus T initial. Now, the right-hand side of this equation we have already seen for the 0 order reaction. What is new is actually this left-hand side. And as I said, this ln stands for the natural log. And we can very easily put that into the equation for a straight line. So we bring that to the other side, and we have ln A final equals minus k times T plus ln A initial. So let's draw that. On my y-axis, I have now ln A and this point here would be my what? What is that? This point here. What is this point? Yeah. It's the Aha. That's the y-intercept, yes. Aha. And people get it absolutely right. It is not my initial concentration. So let me write this down here. A initial, no, it's not. Let me just quickly remove this. It's not the initial concentration. It is actually ln of the initial concentration. And here we have time. And we would get a straight line. Can the line go beyond 0? Can it become negative? Can it go into the negative area? Yes or no? Can it go into the negative area? Tom says no. Michael says no. Okay, everybody agrees on no. Well, what would happen if we've got a point here, down here? What does this mean if we have a point here? It would be a negative, so ln a final would be smaller than 0. Could that happen? Could ln final, could lna be smaller than 0? Alana says yes. Oh. Yes. So ln a final could be smaller than 0. A final can't be smaller than 0. But ln a final can be smaller. So our straight line can be smaller than 0. Does that make sense? Now what is k in this case? What is k? It is the gradient. It is the gradient again. So our k, the gradient, because it goes down, it's negative. So let me just quickly summarize that. We said the equation for our first order reaction, so if we've got dA over dt equals minus k times a to the power of 1. We have ln a final minus ln a initial equals minus k times t final minus t initial. And if we draw a versus time, we get something like that. But if we do ln a versus time, we get a straight line. Or I can say, if we plot ln a versus time, and get a straight line, we know for sure that it must be a first order reaction. Okay? So, let's say I have a simple reaction and I measure what's going on, and I see something like that. A versus time. What's that? What kind of reaction is that? Zero order. Oh, Lauren, why it's a first order? It should be a straight line. Maybe my drawing skills are not that great. If we do ln a versus time, and we get something like that, we know it is must be first. Absolutely right. If we plot a versus time, and we get something like that, what is it? Carl says first order. First order. I tricked you. I'm a bad person. All we know is that this cannot be 0. It can be a first order, but it could also be a higher order reaction. So if we get something like that, Michael says it could be a second order. And you're absolutely right. It could be a second order. All we know in this case, it's not a first order. It's not a zero order reaction. So that's something we need to take into account. Now, last thing I want to do is I want to show you some modifications of this first order equation, because this comes in sometimes quite handy. So we said we have ln a final minus ln a initial equals minus k times t final minus t initial. Now, according to the rules of logarithm, I can combine that. And I can write ln a final divided by a initial. So I need to calculate that first. I need to calculate this ratio a final to a initial first equals minus k times t final minus t initial. Okay? So that's exactly the same as equation 1. Both equations are totally equivalent. I haven't done anything weird. Now sometimes I want this ln gone. I want to eliminate this ln. What do I do in order to eliminate ln? Josh says E. Put both sides as e to the power of. Hey guys, you truly rock. Yes, I love that. So what I do is I put both sides e to the power of. So I have e to the power of ln a final over a initial equals e to the power of minus k times t final minus t initial. And e and ln cancel each other out. So I have on the left-hand side a final over a initial equals e to the power of minus k times t final minus t initial. Or I can bring this a initial to the other side, and I have a final equals a initial times e to the power of minus k times t final minus t initial. And that again is sort of nothing else but another form of writing these two equations that we have up here. So in a way, if you remember the first equation here, this first equation, you get the other two equations, this one and this one, basically for free. It is a fantastic offer. It is actually 3 for the price of 1. And that is only what you get at the University of Kent. So, what reactions actually follow this kind of type? Very often we find it is elimination of drugs, from the bloodstream. So, for example, aspirin follows a strict first order reaction in its elimination from the metabolism. And also, typical first order reactions is anything that has to do with radioactivity. Okay? So, last thing that I want to do with you very quickly is, we said we have ln A final over A initial equals minus K times T. Let's call that T. That's this T final minus T initial. Let's say I want to know how long does it take me to go from 100 gummy bears to 50 gummy bears. Can we calculate that? Now, obviously we can, otherwise I wouldn't do it with you. So let's just simply plug these things in. And I want to know the time. So let's quickly rearrange this equation and say T equals ln A final over A initial divided by minus K. And I've got here equals ln, my final is 50 divided by 100 divided by minus K. Right? So what is ln 50 over 100? This is ln 0.5 divided by minus K. And that is as far as it gets. We can also write this according to the rules of log. We can write this as ln 2 over K. It's exactly the same, it's just the minus goes up there and it turns around the 0.5 into 2. So we can write T equals ln 2 over K. Okay, so that was from 100 to 50. Now I want to know from 50 to 25. How long will that take? Well, I just use my equation here. And I get ln 25 over 50 divided by minus K. And that is, again, ln 0.5 over minus K. And that's the same as ln 2 over K. Hey, wait a moment, there is something weird. We said from 50 to 25, it takes us that amount of time. From 100 to 50, it takes us that amount of time. Both are the same. This is actually what is called a half-life. And very often it is abbreviated as T-half. And for a first order reaction, T-half is written as ln 2 over K. What is ln 2? Can anyone quickly calculate that, please? ln 2? Yep. Excellent. So the half-life of a reaction, you got it right, is T half equals 0.69 divided by the rate constant. And that's incredibly helpful because we can convert a half-life, which we very often can easily measure, into a K. And then we can use this K to do some calculations with it. Now, what I'm going to do in the next session, which will be in 2 weeks' time, next week, I don't think there is a session, but I stand corrected. In 2 weeks' time, I will do a face-to-face lecture where we will go through these concepts and where you will have the opportunity to do some calculations. But please have a look at the kinetics quizzes that have been set up and try to get a little bit of a feel for how you can use these equations. Because they are incredibly useful, and we will come to a little bit of playing around with it. So, if you don't have any further questions, thank you very much for watching. I apologize for the little glitch at the beginning. I think I know what it was. And this time I think it went quite well. So thank you very much and take care. See you soon. Bye-bye.